In this video we're going to look at techniques for multiplying polynomials together, as well as our first look at how we can start to factor out different polynomials. So first we're just going to apply the distributive property. This is something that we've been using for a while, and we're going to combine our knowledge of the distributive property with our knowledge of the laws of exponents to simplify these expressions. So first I have one term here, negative 5x cubed, and I need to distribute this to each term inside the parentheses, just like we would if it was just a number outside. So first we have negative 5x cubed times x squared. My coefficient is going to be negative 5, and then x cubed times x squared, we add the exponents, we get x to the 5th. Then we have negative 5x cubed times negative 10x. So negative 5 times negative 10 is positive 50. And we have x cubed times x to the 1st, which will give us x to the 4th. If we look at this, there are no more terms that we can combine. Our answer is in standard form, degree 5 then degree 4, so we know that this is our final answer. Go ahead and pause the video and try the second example. When we multiply this one, our first term gives us negative 2x cubed y to the 5th. When we multiply the second, we get negative 8x cubed y cubed. And lastly, we get positive 2x to the 5th y to the 4th. Then we have to check the degrees of each monomial to make sure we're in standard form. Our first term has degree 8, second we have degree 6, and then we have degree 9. We need to rearrange these to make sure that we're in a descending order. So we start with the 9th degree, then the 8th, and then the 6th. Now we're going to take a look at what happens when we have more than just a monomial outside. This is one method that we'll use. You won't be asked to specifically use this method. Some people just really like this for a way to visually represent or organize the information that we get when multiplying. This is similar to the rectangles we looked at in the Desmos activity as well. We're going to take each binomial and use it as the dimension or the headings for one side of our table. So if we use 7n minus 4 for the top, we split it by terms, and each term gets its own section. Then along the side, we'll put the other polynomial. So we have 3n for the first term and positive 6 for the second term. Now we fill this in like a multiplication table, or if we think about it as areas. Our side length here is 3n times 7n will give us an area of 21n squared. We do the same thing here. We have 6 by 7n, which gives us 42n. And we continue to multiply the corresponding values to fill in the boxes. So 3n times negative 4 is negative 12n. And then lastly, 6 times negative 4 is negative 24. Now we look for any terms that we can combine. And we have two linear terms. And we write our final answer. So we have 21n squared plus 30n minus 24. And that would be our final answer if we were asked to multiply those two polynomials. Go ahead and pause the video and try the second example. Alright, if we look at this one, we have our trinomial and our binomial. And I find the table method is really helpful when we have polynomials that are larger than two terms, just because there are a lot of different things to keep track of. When we multiply everything out, then we combine like terms. Our quadratic terms end up canceling each other out because they end up being inverses. So in our answer, we only have 25x cubed minus 29x minus 12. The table method is a visual representation of us actually applying the distributive property twice. So when we do this multiplication, we start by taking our first term and distributing it to each term in the other polynomial. So we have 2x times 7x, which is 14x squared. Then we also need to distribute that 2x to this negative 8. So we'd have negative 16x. And now we're done with the 2x. We've multiplied that through to everything in our second binomial. We don't have to do it again. But we also have to multiply everything in that second binomial by negative 7. So we have negative 7 times 7x, which is negative 49x. And we have negative 7 times negative 8, which is positive 56. So now we want to go ahead and combine any like terms, and we're going to end up, ignore the bell, with 14x squared minus 65x plus 56 for our final answer. Go ahead and try the second one on your own. So we take our 5x, we distribute it to both terms in the other binomial. So we end up with 30x squared minus 25x. Then we also multiply that second binomial by 4. So 4 times 6x is 24x, and 4 times negative 5 is negative 20. We can combine those middle terms, and we end up with the final answer of 30x squared minus x minus 20. Now, the last one that we have here is very special because it's one where people tend to make a lot of mistakes, so we're going to try and knock that out early. We spend a lot of time working with exponents where we take our exponent and we distribute it to everything in the parentheses, we square everything, and we're good. But because we have a subtraction sign in the middle, this no longer works. As soon as I start to split up into multiple terms, we have to do a little bit of extra work. So think about when we square something, we multiply it by itself. So I'm actually going to rewrite this as 5x minus 3y times 5x minus 3y. And now I'm going to use my distributive property like we've been doing to see if we get the same thing. So we have 5x times 5x, which gives me that 25x squared, which we had, so we know we're good. But we also have to take 5x and multiply it by negative 3y. So now I have negative 15y. So I'm doing okay. That could disappear, we don't know. But now we have to multiply everything in our second binomial by this negative 3y as well. So negative 3y times 5x is negative 15y. And negative 3y times negative 3y is positive 9y. So for my last step, I have to combine like terms. And we're going to have something in the middle here. So we have 25x squared minus 30y plus 9y. So anytime we square a binomial, we cannot just square the two terms inside. This is wrong. Okay? We have to take the time to expand it out, find that middle term, and see what our final answer is going to look like. The last thing we're going to look at is our first bit of factoring in the unit. And this is where we identify the greatest common factor. You guys have probably found the greatest common factor for just numerical values before. Now we're going to take a look at what happens when we add variables into those terms that we're looking for the factor of. I start with the coefficients. So we have 18, 60, and negative 24. The greatest number that evenly divides all four of those is 6. Now we need to figure out the greatest common factor of my variables. So I want to look for the largest power of x that all three of those have in common. Here I can go up to 5, I can go up to 3, and I can go up to 2. So the largest power of x that I can pull out of all three is going to be x squared. So when you're finding the GCF, you're actually going to look for the smallest exponent attached to any one variable. If we take a look at our second example up top here, again we start with our coefficients. We have 81, 90, and 36. So my GCF there is going to be 9. Now I look at my variables. I have b squared, b, and there is no b here. So if there's no variable term in all three of my terms for a particular variable, that means that I can't have it in my greatest common factor. So there's not going to be a b in my GCF, and my GCF is just going to be 9. Go ahead and pause the video, try either one of the problems below. Take a look and see if your answer matches. Now we're going to use that greatest common factor to break down a polynomial into the product of two factors. I start by finding my GCF. So if you look at this first one, we have 36 and 42. My greatest common factor there is going to be 6. There's no n in my second term, so I can't have an n in my greatest common factor. When I go to factor, I'm going to write my polynomial as a product of the GCF times whatever is left over after I divide or factor out that GCF. So we're going to have 6 times whatever is left when I factor 6 out. So I say, okay, when we factor, it's the same as dividing. So 36n squared divided by 6 is the same thing as 6n squared. Negative 42 divided by 6 is the same thing as negative 7. So my factored form is going to be 6 times 6n squared minus 7. I can check my work by multiplying back out and seeing if I get the same thing that I started with. So 6 times 6n squared is 36n squared, and 6 times negative 7 is negative 42. This works as the polynomials get longer. So if we look at this one, we have 30, 24, and 9. The common factor between 30, 24, and 9 is 3. And then we look at our powers. We have 5, 4, and 2. We take the lowest, so we have n squared. This means I'm going to write a product between 3n squared and whatever is left over. To find those leftovers, we go ahead and factor out 3n squared. So 30 divided by 3 is 10, and n to the 5th divided by n squared is n cubed. 24 n to the 4th, factor out the 3n squared. 24 over 3 is positive 8. N to the 4th over n squared is n squared. And we do our last one. 9 divided by 3 is positive 3. N squared divided by n squared is 1, so we don't have an n in this term. We leave it as is. Go ahead and pause the video and try either one of the last examples. Go ahead and check your work. We start by finding the greatest common factor of the coefficients, then deal with any variables. In the problem on the left, there's no n in our last term, so that means there's no n in our greatest common factor. We divide each term by 3, figure out what's left over, and write our product. In the second one, it's a little more complicated because we have more variables to deal with, but still the process remains the same. Start with our coefficients. We see that we have a GCF of 4. Then we have x to the 1st, x cubed, and x squared. So our lowest power is x to the 1st. For y, we have y to the 8th, y to the 5th, and y cubed. So we go with y cubed. Factor it out and see what we get left over.